The most dangerous piece of equipment in the ocean may be the one you trust completely, because every regulator, pressure gauge, diving cylinder, submersible window, seal, hose, cable, and life support system has something in common: a limit. And the deeper you go, the less forgiving that limit becomes. At the surface, a tiny defect may mean nothing. At extreme depth, that same defect can become the beginning of a catastrophic chain reaction. The frightening part is that elite equipment does not have to be poorly designed to fail. It can be expensive. It can be certified. It can be tested. It can have worked perfectly 100 times before and still reach a point where physics wins. This is the fatal math. Why elite gear hits a breaking point. Imagine descending into the ocean. At 10 meters, the pressure around you is roughly twice what you experience at the surface. At 20 meters, roughly 3 times. 30 meters, about 4 times. And the numbers keep climbing. The deeper you travel, the greater the pressure pushing against everything separating you from the ocean. Your mask, your suit, your hoses, your electronics, your breathing system. And if you're inside a submersible, the entire pressure hull surrounding you. Water doesn't need to find a large opening. It only needs weakness, a microscopic crack, a damaged O-ring, metal fatigue, a connection that wasn't seated perfectly, a material that has been stressed one too many times. At depth, the ocean begins doing the rest of the work. And that is where the math becomes terrifying. Engineers often talk about something called a safety factor. If a component is expected to experience a certain load, it may be designed to survive significantly more than that load. That sounds reassuring, and it should. Safety factors are one reason sophisticated diving equipment is remarkably reliable. But a safety factor is not immortality. Suppose a component is designed to tolerate forces far beyond what it normally experiences. That margin exists under particular assumptions. Known material properties, proper maintenance, correct installation, expected temperature, expected number of pressure cycles, expected operating conditions. Change enough of those assumptions, and the margin can begin disappearing. Slowly, quietly, sometimes invisibly. The equipment may still look perfect from the outside. Think about bending a paper clip. Once, nothing happens. Twice, still fine. Keep bending it back and forth, however, and eventually it snaps. You didn't suddenly become stronger. The metal became weaker. That is a simplified example of fatigue. Many pieces of serious underwater equipment undergo repeated loading and unloading. A submersible descends. Pressure rises. It returns to the surface. Pressure falls. Then it does it again. A diving cylinder is filled, used, filled again. A flexible hose is pressurized and depressurized. A seal is compressed repeatedly. One cycle might cause no meaningful damage, neither might the 10th or the 100th. But repeated stress can create microscopic changes inside certain materials. Those changes can accumulate. And this creates one of the most dangerous sentences in engineering. It worked last time. Because working last time does not guarantee the same amount of safety margin remains today. Now consider another problem. Pressure doesn't always attack equipment evenly. Geometry matters. A perfectly manufactured structure can distribute forces extremely well. But real-world equipment is never mathematically perfect. There may be tiny manufacturing variations, scratches, corrosion, small dents, machining marks, previous repairs, material imperfections. Even seemingly minor damage can concentrate stress into a smaller area. Engineers call these stress concentrations. Imagine pushing down evenly on a thick sheet of ice. The load spreads across the surface. Now imagine striking one tiny damaged spot. The local stress becomes much greater. At extreme pressure, a small imperfection can become disproportionately important. And once a crack begins propagating, failure may accelerate far faster than a human can react. This is where depth changes everything. At recreational diving depths, divers still depend completely on their equipment, but many failures may provide warning or allow some response. A leaking mask can be cleared. A free-flowing regulator can sometimes be managed. A failed primary regulator may be replaced with an alternate air source. A buddy can provide breathing gas. Training is built around redundancy because divers understand that individual systems can fail. But as operations move deeper, the consequences become increasingly severe. At extreme depth, you may not simply swim to the surface. The pressure change itself makes that impossible. Decompression obligations can trap divers underwater, even when equipment problems are developing. In saturation diving, workers may live under pressure for days or weeks. In submersibles, occupants may be completely dependent on the vehicle maintaining its structural integrity. Suddenly, the machine isn't helping you survive. The machine is your environment, and if that environment disappears, there may be no second chance. Consider an O-ring. It might cost almost nothing compared with the equipment surrounding it, yet that tiny ring may be responsible for keeping high-pressure gas inside a system or seawater outside one. When installed correctly and maintained properly, O-rings are extremely effective. But they have enemies: dirt, hair, sand, cuts, chemical degradation, incorrect lubrication, improper sizing, heat, age, and human error. A SEAL doesn't care that the entire system costs $1 million. If the SEAL's integrity is compromised, the ocean sees an opening. This is one of the strange truths of advanced engineering. The weakest component can determine the survival of the strongest system. The same principle applies to breathing equipment. A modern diving regulator performs an extraordinary job. A scuba cylinder may contain breathing gas at extremely high pressure. The regulator reduces that pressure and delivers gas at a pressure the diver can breathe. It does this repeatedly, breath after breath, dive after dive, usually with astonishing reliability. But regulators contain moving parts: seats, springs, diaphragms, O-rings, valves, hoses, connections. Each component has specifications, each has wear limits, and every system requires maintenance. This is why professional divers don't simply ask, "Is this good equipment?" They ask, "When was it serviced? How many dives are on it? Has it been damaged? Has anything changed? Is there a backup?" Because reliability isn't a permanent quality. It is something that must be continuously maintained. Then, there is corrosion. Saltwater is relentless. A tiny amount of corrosion may seem cosmetic, but underwater systems combine salt, moisture, metals, pressure, and sometimes electrical systems. That creates conditions where degradation can become serious. Different metals can react with one another. Protective coatings can be damaged. Threads can weaken. Electrical connections can deteriorate. Water can invade spaces where it was never supposed to exist. And corrosion doesn't always announce itself dramatically. Sometimes the equipment keeps functioning, until suddenly it doesn't. Temperature introduces another variable. Deep ocean water is cold. Materials can behave differently as temperatures change. Seals can stiffen. Battery performance can decrease. Gas behavior changes. Lubricants behave differently. Components contract. And breathing gas expanding through a regulator can produce additional cooling. Under certain conditions, icing can contribute to regulator malfunction. Again, none of these factors operate alone. That's the important part. Real disasters often aren't caused by one spectacular mistake. They're caused by several small problems aligning. Cold water, a partially worn component, a minor leak, higher than expected workload, increased breathing demand, reduced visibility, stress, and suddenly an ordinary equipment issue becomes an emergency. This leads us to one of the most important concepts in survival engineering: redundancy. If one failure can kill you, engineers try to create another layer. Divers carry alternate regulators. Technical divers may carry completely independent breathing systems. Commercial operations use backup communication, backup power, emergency gas, reserve systems. Submersibles may use multiple communication methods, emergency ballast systems, independent life support equipment, and redundant control systems. But redundancy has a hidden weakness. two systems aren't truly independent if the same event can destroy both. Imagine having two flashlights. That sounds redundant. But if both lights use batteries from the same defective batch, your redundancy may be an illusion. Two air supplies are valuable, but not if both depend on the same damaged manifold. Two computers can be useful, but not if one electrical failure disables both. True redundancy requires asking a darker question. What single failure could take everything away? Engineers call this a common mode failure, and it can defeat systems that appear incredibly safe. Aircraft engineers worry about it. Nuclear engineers worry about it. Spacecraft designers worry about it. And deep-sea engineers absolutely worry about it. Because stacking multiple safety systems together does not help if all of them depend on the same vulnerable component. That is why complicated systems must be examined as complete networks, not simply as individual pieces of impressive technology. Humans introduce another problem: confidence. The better equipment becomes, the easier it can be to believe failure is impossible. That creates something called risk compensation. When people feel safer, they may sometimes accept risks they would otherwise avoid. A stronger vehicle may encourage someone to travel deeper. A better dive computer may encourage a more complicated dive. Improved navigation equipment may encourage exploration farther inside an overhead environment. Technology expands what humans can accomplish, but it also moves the boundary, and eventually the new boundary becomes dangerous again. Elite gear doesn't eliminate risk. It allows us to operate closer to risk. Now imagine a diver preparing for an extreme dive. Every piece of equipment is premium. The regulators are excellent. The cylinders are inspected. The computer is advanced. The lights are powerful. The diver has years of experience. It feels like the safest possible setup. But then, the dive begins. A current is stronger than expected. The diver works harder. Gas consumption increases. Visibility deteriorates. A small leak begins. Nothing catastrophic yet. The diver continues. Minutes later, the remaining gas reserve is smaller than planned. Stress increases. Breathing accelerates. Gas consumption rises again. Now the diver is no longer dealing with one problem. The diver is dealing with a feedback loop. Higher workload creates higher gas consumption. Lower gas supply creates stress. Stress creates faster breathing. Faster breathing consumes more gas. Suddenly, mathematics begins closing the escape window. That is why experienced technical divers don't just carry good equipment. They carry plans based on numbers, turn pressures, gas reserves, decompression schedules, maximum depths, maximum penetration distances, and predetermined abort conditions. The goal isn't to prove the equipment can survive. The goal is to avoid discovering where it stops surviving. Perhaps the most frightening failures happen when there is almost no warning. Certain structural failures can progress extremely quickly once a critical threshold is crossed. A component can tolerate stress, and tolerate stress, and tolerate stress. Then one additional increment pushes it past the point where the material can recover. The transition between safe and catastrophic may be incredibly small. That's what makes the phrase breaking point so accurate. Before that point, the structure exists. After it, the structure may no longer be capable of carrying the load. At extreme pressure, the energy involved can be enormous, and events may unfold faster than the occupants can understand what happened. This creates a fundamental rule of deep-sea survival. You never want to operate at the actual limit. If a system's theoretical maximum is X, responsible operations generally stay well away from X, because the real world contains uncertainty, manufacturing variation, age, damage, measurement errors, unexpected loading, human mistakes, unknown conditions. The safety margin exists because engineers know they cannot predict everything, and when people repeatedly consume that margin, eventually they may encounter the variable nobody anticipated. There is another mathematical enemy: probability. Imagine a mission with one critical component that has a tiny chance of failure. That might seem acceptable, but complicated operations can contain hundreds or thousands of components. Now, repeat the mission again, and again, and again. The probability of encountering some failure over time begins increasing. This doesn't mean repeated operations are automatically reckless. It means inspections, maintenance, replacements, testing, and operational discipline become increasingly important. The ocean doesn't care how many successful missions came before. The next descent begins at zero. This is why professionals can seem obsessed with checklists. Check the gas, check the seals, check communications, check emergency systems, check batteries, check pressure, check connections, check the backup, then check the backup to the backup. To someone watching from the outside, it can look excessive. Until you understand the environment, deep underwater, inconvenience and catastrophe can be separated by one forgotten step. A loose fitting at the surface might cause a delay. At depth, it can become a life support failure. And perhaps that is the real lesson behind elite equipment. The technology isn't weak, quite the opposite. Modern underwater systems allow human beings to survive in places our bodies were never designed to enter. We descend beneath hundreds or thousands of feet of water. We explore caves where sunlight has never reached. We work on pipelines and structures under immense pressure. We send vehicles into some of the deepest places on Earth. That's extraordinary. But every one of those achievements is temporary. For a few minutes or a few hours, engineering creates a tiny bubble where human life is possible. Outside that bubble is an environment capable of crushing structures, flooding electronics, exhausting breathing gas, and defeating human physiology. The deeper we go, the thinner the margin becomes. So, when you see a diver wearing thousands of dollars of equipment, or a sophisticated submersible disappearing beneath the waves, remember this: price doesn't defeat physics, experience doesn't repeal mathematics, and yesterday's successful dive does not guarantee tomorrow's successful return. The safest explorers understand something that the ocean teaches repeatedly. Equipment should never be trusted because it is expensive. It should be trusted because it has been tested, inspected, maintained, backed up, and operated within its limits. Because eventually, every material has a breaking point. Every machine has a limit. Every safety margin can be consumed. And thousands of feet beneath the surface, you may never get the opportunity to discover that limit twice. The ocean doesn't need your equipment to fail completely. It only needs one weakness to reach its breaking point.